All right, Math 152, 6.3 confidence intervals for population proportions. So we've covered confidence intervals for population mean in a previous section. Now we're looking at proportions. So remember, proportions means we're dealing with a passing rate. A passing rate of P. So we have no sample mean, no sample standard deviation. No sample mean, no sample standard deviation. All right, the probability of success in a single trial of a binomial experiment is P. This is a passing rate for the population. The point estimate for P, the population proportion of success, is given by the proportion of success in the sample. So we had sample mean for population mean. Now we have sample proportion, or P hat, for the population proportion. To find P hat, you take your number of successes and divide it by your sample size. Number of successes divided by sample size. So X is the number of successes. So how many things surveyed or how many things collected has that characteristic, and then out of your total. They could call it sample size, they could call it trial, they could call it N. They all mean the same thing. What is your sample size? All right, the point estimate for population proportion of failures is Q hat. So we have P hat for success. Q hat, which is the opposite of P hat, is our proportion of failures. The symbols P hat and Q hat are like so. All right, so let's find our point estimate. Remember, point estimate is our starting point. We're trying to guess what the population looks like, and we're using population proportion this time. And we're going to base that off of our sample. In a survey of 540 U.S. adults, 500 U.S. adults, 378 say they plan to travel this summer. Find a point estimate for the population proportion of U.S. adults who plan on traveling this summer. All right, so we point estimate means P hat. Point estimate means P hat. How do we calculate that? How many people out of the 540? How many people out of the sample? So 378 out of the 540 sample have that characteristic. So that is 378 divided by 540. So using Excel, using the same thing, equals 378 divided by 540. This is 0.07. We want to use 4 decimals. If they don't specify how many to use 4 decimals. Okay? So this means the point estimate for the population proportion, I don't have a lot of room. Just want to make sure I give you enough room. I'll give you an understanding what this means. Proportion of U.S. adults who plan on traveling this summer is 70%. Sorry, it looks a little crazy. I want to make sure I wrote that down somewhere. So the point estimate for the population proportion of U.S. adults based on our sample. So our sample was 70%. We think P is 70%. Adults who plan to travel this summer is 70%. Okay, so we know our sample says 70%. we're pretty confident that the population proportion is 70%. That's what that means, okay? Confidence intervals for a population proportion. So a C confidence interval for the population proportion, P, and the probability that the confidence interval contains P is C. This is our confidence level, assuming that the estimation process is repeated a large number of times. So that means we're going to be 90% confident, 95% confident. We're going to be that confident that our answer is somewhere in this interval. All right, so this is what our interval looks like now. This is our point estimate minus margin of error, point estimate plus margin of error. Don't forget, this sets population proportion, and we got that from p hat. So we're saying p hat is what we received. We think the population is what is actually happening. So we got p hat. We think this is happening for our population as well. So we're dealing with a different type of data set. So our E is going to change for the formula. This is on your formula sheet. E is equal to ZC square root of P hat times Q hat over N in the margin of error. So we talked about ZC a little bit last section, so we're actually going to use it this section. So confidence interval P hat minus E, P hat plus E. That's how we're going to get our actual interval. So let's look at finding the critical value ZC. We found TC using inverse T in table 5. Just as a reminder, we're going to use inverse norm in the calculator or inverse norm in the Excel or table 4. So let me go over to table 4 real quick to show you a lot of times that your ZC is listed. So here is your formula sheet. Table 4, notice at the bottom of the formula sheet, there are these values. I'm not sure if you can see my screen. But down here at the bottom, those are our ZCs. Those are our common ZCs. So we're going to calculate 0.90 just to show you how to actually calculate this. So ZC, remember, you need a negative and a positive answer whenever you are given the answer of a critical value. You even see this on table 5. You need a positive and a negative answer for a critical value. Okay, so they ask you for critical value. You need to give them both. If you're working in the middle of your problem, you don't have to give both because we're going to get a negative and a positive whenever we actually work the problem out. Okay, and I'll show you what that looks like. All right, so inverse norm, norm.inv or table 4. So the table said that Z90 was 1.645, I believe. Forgot that quick. So let's look at the calculator and then we'll look at what we'll just do with the calculator because it's right here. I don't want to switch screens too much for Excel. So Excel, you're going to put in norm.inv or norm.sinv. Norm.s.inv. 1 minus c divided by 2. Notice that's in parentheses because so you're going to do the same thing we're doing with our area. So second vars is where inverse is. Second vars, inverse norm is number 3. So again, if you're using Excel, you're doing the same thing I'm doing. 1 minus 0.95 divided by 2. If you have the left, right, center calculator, you're just going to put in your C. You're not going to do 1 minus C. Okay? So non-left right centered calculators in Excel, we're doing the same thing. 0, 1 is our mean standard deviation because we want a z-score. Oop, say the wrong one. 1.96 was what it said in the table. Couldn't remember, sorry, that quick. Oh, wait a minute. I did have it right. Negative 1.645, I put 95. 95 is the most common. So a lot of times I'll just do it just off of repetition. But yeah, we're finding Z90, which is negative 1.645. So for the calculator, inverse norm, 1 minus 0.90 divided by 2, or inverse norm, 0.90, and make sure you put center. And then for Excel, for norm.inv, now if you use norm.s.inv, all you have to do is put in your area, and it will automatically just give you your answer. But 1 minus 0.90, parentheses, divided by 2, comma 0, comma 1. If you see that one or not. And we all come up with the same answer. So notice the calculator gives you a negative, Excel will give you a negative, so you're going to have to make it negative positive. Normally we do go to 2 decimal places for Z, but if you remember from the table, they do 3 for this particular one. Not sure why, so I just kept it at 3. So you can do 3 decimal places or 2 decimal places. You should be fine. All right, that's how to find ZC. And you're going to need ZC to calculate if you're going to either find the critical value, just one critical value, or you're going to do these problems manually or in Excel. So let's look at how we construct a confidence interval. We identify the sample statistic X, N, and X. Find a point estimate, P hat, X divided by N. We verify that the sample distribution, P hat, can be approximated by normal distribution. So instead of central limit theorem, we have to check to make sure we have enough sample. So we multiply N times P and N times Q to make sure we have at least 5 in our sample size. So we need at least 5 successes and 5 failures in our sample size. And we do this because we don't have a sample mean, so we can't check the central limit theorem. Don't have a sample mean, can't check the central limit theorem. So we're going to verify that the sample distribution P hat can be used. 5 successes, 5 failures. So find the critical value ZC that corresponds to the given level of confidence C. Table 4, which I just showed you. Or we can use inverse norm from above or norm.inv. All right, then find the margin of error, E. That's our formula. And then find the left and right endpoints and form the confidence interval with P hat minus E, P hat plus E. Okay, so let's look at the different ways to work these out. We're going to work out one example. building on the example that we've had thus far. All right, find the confidence interval on a stat test 1 prop z interval. Remember, because we have p hat. Enter the number of successes x, enter the sample size n, enter the confidence level and C level, and then press calculate. Let me make a note right here. I forgot to make a note in my notes, but this must be a whole number. So you have to actually have how many successes you have. Sometimes your problem may give you p hat, and you have to find out how many people you have. So if that's the case, x is normally given to you, but if it's not given to you, to find x, you're going to multiply your sample proportion times n and round to a whole number. Round to nearest whole number. You're not going to round up. You're going to round to the nearest whole number. So if it's 2.3, you're going to round to 2. If it's 15.1, you're going to round to 15. So use this whenever they give you a p hat in a problem, as opposed to giving you how many people it is. So they may say 50% of your sample size wears glasses. So you're going to multiply 50% times your sample size. Okay. Press calculate. Same thing for Excel, but it's a little different in Excel. Excel, you want to identify your X, your N. Calculate your P hat and Q hat. So we have the formula X over N. And then Q hat is 1 minus this, so opposite of that. And then we're going to find our margin of error, because they don't give it to us like they do in descriptive statistics. They don't give it to us, so we got to find it. So formula is ZC times square root P hat times Q hat divided by N. P hat times Q hat divided by N. All right, so let's work this out. In a survey of 540 U.S. adults, 378 said they plan on traveling this summer. Construct a 95% confidence interval for the population proportion of U.S. adults who plan on traveling this summer. So first, I need to calculate P hat and then determine if I have at least 5 successes and 5 failures out of this 540. We've calculated this ahead of time, so 378 divided by 540. We found that to be 0.7. So how many out of our sample size do we see as being successes? This is 540 times 0.7. So 378 people are successes, and that makes sense. We just got that. And times Q hat, it's 540 times 0.3. That is our Q hat, 0.3, right? 0.7 and 0.3, they're opposites, or complements, excuse me. 162. So I have, out of the 540, 378 are successes and 162 are failures. Okay, so that's at least 5 and at least 5. We can do our problem. All right, here we go. So we're going, in the calculator, I'm going to do the technology first. So we're going to 1 prop Z, interval, 1 prop Z interval in the calculator. You're going to put in your X, your N, your C level, and then calculate. Your X, your N, your C level, then calculate. So notice we didn't have to find our margin of error because the calculator is going to calculate it for us. So I'm going to stat, test. I go down. There's my one prop C interval. Right there. See it? One prop C interval. Don't mix it up with one prop C test. We're doing that next chapter. One prop C interval. Our X is 378. Our N is 540. Hit calculate. And there is our interval. It didn't tell us where to actually round off or anything, so I'm going to keep all of them. All the digits. This confirms my p hat and confirms my n. All right, let me switch over to okay, so we need to calculate p hat. I don't know why this is uppercase. P hat, which is equal to, it's not equal, x divided by n for Excel. X divided by n. X divided by n. And then q hat is equal to 1 minus this cell. The opposite of that, 1 minus that cell. I'm taking this from your notes. So to find your margin of error, E, we find the ZC of 95. So ZC 95, I believe that is 1.96. I can't see I'm pulling the sheet. Times the square root P hat Q hat divided by N. So we have P hat times Q hat divided by N. P hat Q hat divided by N. P hat Q hat divided by N. So to get our lower confidence interval, we're going to take equals P hat minus E. So P hat minus E and our upper confidence interval, our upper endpoint, is equal to P hat plus E. P hat plus E. I did it wrong. There we go. And you're going to take 4 digits out from that as well. Okay. Go back to my camera. Try to make it focus. There we go. All right, back in focus. So in Excel, we had to actually use the formula Z95 times square root, and you're going to put your cells in, but I'm going to put this in for now so you can see, you know where I'm getting those numbers from. That was P hat times Q hat over N. You're going to actually click those cells. All right, to work this out manually. You can skip over this if you don't want to work out manually. Remember, we need P hat minus E, P hat plus E as our interval. That's a comma, sorry, it's a comma. So P hat we know is 0.70 or 0.7. E is what we're going to have to figure out. And on the Excel, it does, we do figure that out. We do actually work that out. So Z95 times the square root of P hat Q hat over N. That's 1.96 times, I'm getting that number from either inverse norm, norm.inv, or table 4. So I'm getting that number from the bottom of table 4. Square root of 0.7. I'm putting this in parentheses because I have a lot of decimals. That's the only reason. You don't have to put this in decimals. Okay, 1.96 times, like Excel, square root of 0.7 times 0.3 divided by 540. Because this is all multiplication and division, you don't have to worry about parentheses. And that gives us a margin of error of 0.039. 0.039. Or 0.0387. How do they tell you to round? That's how you're going to round. All right, last part. Finding a minimum sample size. So given a confidence level C confidence level, and a margin of error, the minimum sample size needed to estimate P is, and then here is our formula. So this formula is using P hat and Q hat as our information is given. All right, and you're going to need to know that because there's two different ways you can do these finding minimum sample sizes. This is in your formula sheet under chapter 6. This is E is a percentage. Your margin of error will be a percentage. Okay, my internet just went out, so sorry about that, y'all. So E is a percentage. They're going to give you E. You're not going to actually have to calculate E. They're going to give you E. E is a percentage. And if the answer is not a whole number, then round N up. Okay. The formula assumes that you have an estimate for P hat and Q hat, meaning they tell you what your preliminary estimate is. So preliminary estimate. Or something they already know. If not, you're going to use 50-50. 50% chance of success, 50% chance of failure. So let's look at what that looks like in one problem and how it affects your problem. So you're running a political campaign and wish to estimate with 95% confidence the population proportion of registered voters who will vote for your candidate. Your estimate must be accurate within 3%. So that's our margin of error, 3% left or right of the true proportion. Find the minimum sample size. So here, they gave us our level of confidence, but they don't give us our P hat. So this is a 50-50. We'll look at the next one that gives us a P hat. So E is telling us we can only be off by 3%. Or we think we're only off by 3%. So according to our formula, N is equal to P hat, Q hat, ZC over E squared. So only this is squared. And this is actually Z95. They don't give us a passing rate, so 50-50. Z95, again, I use it so much, I normally just default to 1.96. This is your, if you don't have a Z, that will be your Z, 1.96. And we have our margin of error. So this is 0.5 times 0.5 times 1.96 divided by 0.03 squared. If you're in Excel, just put this into your cell. Remember, this is 0.03, not 0.3 squared. 1067.11 if we have to round. So this one did not come with a whole number, so I have to round. If it comes with a whole number, you don't have to round. But here it's telling me to round. So I have to round up. Even though this is 0.11, I have to round up to the next person. Okay. Let's look at the same problem, giving us a preliminary estimate, and then we're going to compare. You're running a political campaign and wish to estimate with 95% confidence the population proportion of registered voters who will vote for you. Your estimate must be accurate within 3% of the true proportion. Study. So here's our previous information. So this time our P hat is 0.31. Q hat, so just subtract those two. 1 minus 2.31 is 0.69. And to get Q hat, you always subtract from 1. And then we have our 1.96 divided by 0.03. 0.03, not 0.3. So I'm going to put parentheses because all these decimals, you don't have to. Just feel weird not doing it. You do have to put a parentheses around this because our formula had that. Divided by 0.03. I did the caret button. or you can just hit the squared button. $913.02. So this looks like a whole number, but it's not. It still has a decimal on the end. If it was a whole number, it would come out to be 913. That's it. So because this is a number that needs to be rounded, I have to round up. Okay, so for preliminary estimates or for p-hats and sample size, you need a larger sample if no preliminary estimate is available. And that makes sense. If you don't know anything, you're going to need more sample to prove what you're doing, to prove if you're right or wrong. If we have some information, we don't need as much of a sample because we have the information. All right, so last part. Finding minimum sample size to estimate the mean. So one way to prove the precision of an estimate without decreasing the level of confidence is to increase the sample size, as said before, given a C level confidence and margin of error E. The minimum sample size N needed to estimate the population mean. So we had population proportion before, now we have population mean. Is this formula, N equals, notice everything is squared in this one, so be careful, everything is squared in this one. So E will not be a percentage. And here you have a population standard deviation. So E will not be a percentage. And then we have a population standard deviation. So what that looks like. If N is not a whole number, then we round N up to the next whole number. If N is unknown, you can estimate using S as well. So you can use this using S if they provide you with the S and you have at least 30 members. So if it meets that central limit theorem. So a researcher wants to estimate the mean number of hours spent per week on required athletic activities by all student athletes in the conference. How many student athletes must be included in the sample to be 95% confident that the sample mean is within 0.5 hour of the population of the mean? Assume the population standard deviation is 2.4. Okay, so we're looking at trying to figure out how many athletes do we need to be confident in our interval that we're about to embark upon. All right, so this formula is Z95. Again, 95 is used a lot. Z95 is 1.96. We'll calculate this as well. We'll calculate this to make sure you're good with knowing how to get this. Time standard deviation, population standard deviation. See, I got all those dots. That's why I didn't want to use dots. And then we can only be off by 0.5 hours. So it's not a percentage that they're giving us. They're giving us an actual unit. So this is 1.0 parentheses because the formula has parentheses. 1.96 times 2.4 divided by 0.5 squared. Make sure it's 0.5 and not 0.05. Okay, 0.5. Enter. 88.51. Notice I'm not rounding, I'm just putting the number down. And then I'm going to round. I'm not sure if I covered this in the previous video, but let me cover this real quick about confidence intervals. This is a little, if you stay to the end, and you get this little tip. Sometimes they will give you the answer and they want you to find the sample mean and margin of error. So you can work backwards. So let me show you. So let's say we have this interval. I think I have one written down here, 21.61, 30.15. They give you the interval. And they want you to find your point estimate and your margin of error. They want you to find point estimate and margin of error. And point estimate is your guess for your sample mean or sample proportion. So if they ask you that, you're going to add your endpoints divide by 2. So to get sample mean, you're going to add your endpoints, divide by 2. To get margin of error, you're going to subtract your endpoints. Divide by 2. So kind of like Jeopardy, they may ask you, they may give you the answer and tell you to give me the question. Give me, what did you start off with? Give me your margin of error. And this is how you complete it. So let's look. Adding my endpoints, 21.61 plus 30.15 divided by 2. Notice I'm doing this separate. And this makes sense. This is my sample mean, which is the middle of my interval. And that is the middle of my interval, 25.88. So we're going to subtract our endpoints. Going up. Copy that. We're going to subtract the endpoints. Divide by 2. I'm going to make this positive because your margin of error needs to be a positive number. So saying how far off you're going to be, just make it a positive number. So that's how you actually calculate your sample mean and margin of error if they give you the interval. Again, I'm not sure if I showed you that, so I'm going to show you here. And if I showed you before, just act like you've never seen it. All right. So remember, all problems and images are taken from Elementary Statistics, Picture in the World by Larson Farber, 8th edition.